Hey there. Today I'm going to be talking about my project on exploring convolutional neural network architectures using the MNIST digital classification problem. The MNIST dataset is a collection of handwritten digits from 0 to 9. Training machine learning models to classify these digits is a de facto hello world of computer vision deep learning. So my goal here is to use this well-understood framework to run through a few CNN architectures and look through their training performance. I downloaded the MNIST dataset from Kaggle. The data itself consists of training images and associated training labels, and the same for test images and labels. The images and labels were encoded as IDX3 UByte and IDX1 UByte files, respectively, so I also used a provided data loader, also found on Kaggle, from the same author to read in the data. Because the MNIST dataset is pretty popular, it's well known to be quite clean already. But I did run through a couple of EDA, that's exploratory data analysis steps, just for the sake of best practices and to build good habits. Looking at the data, there are 60,000 labeled training images and 10,000 labeled test images. The images themselves are 28 by 28 grayscale images with pixel values ranging from 0 to 255. I also plotted the class distributions here on the right, you can see, for training and test sets, just to check for any class imbalance. There's some slight variance across the class representations, but there isn't really enough skew to make me consider any sort of class normalization that might be necessary. Maybe if one of the training classes had like 10,000 members while another had half that, I would consider rebalancing the training data. But that wasn't necessary here. If you read through my notebook, you'll also see that I do a quick check just to make sure all of the training data and test labels are, in fact, digits from 0 to 9, and there's no sneaky letters or other characters in there. Again, this is superfluous as the MNIST dataset is already known to be clean, but it's always good to double check things. I'm not going to show it here in this presentation, but if you're following along in my notebook, you'll see that I built some PyTorch datasets and data loaders just so I can send the data to my GPU properly once I start training, but this is standard for building models with PyTorch, so nothing special worth showing off. Now for the fun stuff. This slide is an overview of the 3 models that I trained in this project. In summary, I start with a very simple CNN with 2 convolution layers and bump it up to 4 layers for a slightly deeper model. And the last layer I build is a mini version of the VGG16 architecture, named after the visual geometry group at Oxford. The VGG model is specifically built as a relatively simple model for classification tasks. I chop it down a little bit. So instead of the nominal 16 layers from VGG16, I have a total of 9 with 7 convolution layers and 2 dense layers at the end. So it's more, I guess, of a VGG9 model, if you wanted to call it something. I refer to it as my mini VGG model throughout this presentation. As a quick note, I use ReLU activation in all of these models. You can pause here if you want to read the summary table in depth, but I'll go into each model a bit more up next. So, starting with the simple model. This model has, again, 2 convolution blocks and 2 dense layers. The first convolution block has 1 convolution layer with 32 3x3 kernels, filters, 32 filters with 3x3 kernels, and max pooling with a stride of 2. The next block is built much the same, with 64 filters in the convolution layer. The first dense layer is a flattened 128 units, and the second layer is 10 units for the output, which is our digits 0 through 9. The deeper CNN, again, is highly similar, with an extra convolution layer in each of the convolution blocks for a total of 4 convolution layers. The first fully connected layer has 256 units here, and again condenses down to 10 for our output. The VGG is a little more complicated and scaled up. It again has it has 2 convolution blocks that have 2 layers, but it adds a third block with 3 convolution layers before pooling. The blocks use convolution layers with 64, 128, and 256 filters respectively. You'll also notice that I include batch normalization after each of the convolution layers. It has a similar dense layer structure, with the first dense layer having 512 units and the output layer having 10, but you'll see that I didn't write it here, but you'll see that I added in some dropout to, again, protect against overfitting. This larger model with more layers increases risk of overfitting. So I try to mitigate that a little bit with batch normalization and dropout. So on to training. During training, I logged loss and accuracy for both train and test sets over 30 epochs using TensorBoard. As you can see in the top left subplot here, all of my models drop loss pretty quickly over the first 7 epochs. Shortly after 10 epochs, the models all appear to finish learning the data as they converge to 100% training accuracy and thus 0 loss. I didn't stop them early here. I didn't build that into my training loop. Probably should have. Because it's not super useful to continue training after the model converges. If anything, it only really risks overfitting. With training complete, I ran some performance assessments just to check out specifically how each model handled the task. For the simple CNN, we'll start there. It had a final accuracy of 99.31, which makes only 69 out of 10,000 test images misclassified. That's pretty good for what's a very simple model that took not a lot of time to train at all. It was anyway for a simple model. As you can see in the confusion matrix on the right here, the biggest source of our error was misclassifying 5s as 3s with 7 total misclassifications in that one-way pairing. There were a number of other misses, such as getting 2s and 7s confused in both directions. You can see on my image is flipped. Anyway, you can see across the diagonal both 2s and 7s and 7s and 2s get misclassified. As well as struggling to identify 9s just as a variety of different numbers. You can see there 4s and 5s in particular. I have some examples of misclassified digits here with the bad predictions in parentheses at the bottom. You can see this first number. Here. There you go. First number is supposed to be a 6. The model called it a 5. I'm guessing that has to do with the curve in the model. This one, I can actually see this misclassification. It is supposed to be a 6, but the model was called a 0. Again, it probably is because of this completed loop. I'm not sure how the neural network is seeing that, but the closed loop might make it think that it was a 0. This one, supposed to be a 9, looks like a 4. Honestly, if you showed me this number, I'd probably call that a 4 too. You can see that loop on the 9 is not closed. This 7 here was called a 2. You can see that the line crossing through it is a little low down and it's not very complete, so maybe it saw that as the extra thing that sticks out on the 2. You can see this 6 here. If you didn't tell me these were just numbers, I think this was a lowercase gamma. And again, for the lower, you can kind of spot out where the mistakes happen. Again, you have a number of these 9s that are misclassified, specifically as 4s, and then vice versa for the 4 as a 9 here. So you can kind of see why it's making these mistakes. These aren't super simple examples that it's missing. So again, performance is overall pretty good. The deeper CNN, slightly better training accuracy at 99.38, only missing 62 of the 10,000 images. That isn't much more than the simple model, but I did train these models a couple of times, and the deeper model was consistently a smidge better than the simplest model. So that is a real increase, even though it is slight. You might notice, however, that the confusion matrix looks a lot similar, or highly similar to the simple models. That is because it actually made a lot of the same mistakes, just slightly fewer. If I flip back and forth between these, you can see that those are different confusion matrices. They're just highly similar. And again, if we go through these digits, you can see a lot of the same mistakes. This is a 4 that was called a 2. I'm assuming that's because it kind of comes down and out, which is characteristic of 2s. If you told me that was super sloppy, I'd call it a 2. Probably wouldn't recognize it as a 4 either. This is an example of kind of why you see a lot of that misalignment with 5s and 3s. Honestly, I would probably call this a 3 too. It looks like it comes kind of like that instead of just the down and around as a 5. So you can see where that mistake comes from. Again, the 7, the crossbar is a little low there, and it's a little rounded on top, so I'd call that a 2. And this 9 is a little slanted, call that a 7. So you can see these aren't trivial examples that the models are missing. So overall, I think performance is still pretty good. Moving on to the mini VGG, as I call it. Again, our most complex model thankfully also had the best performance with a grand total of 40 misses out of 10,000, giving us an accuracy of 99.6%. Across the board, it performed a little better than both of the prior models with a maximum one-way confusion of 4 samples for any true label predicted label misses. The prominent errors here seem to be concentrated around numbers that heavily feature curves and loops, like 5s, 6s, and 9s. Again, you saw this in the previous ones as well, but this really also only erred on those. So again, we can see a 3 that was called a 5 incorrectly. It has that roundness at the bottom, a little flat on top. Maybe that's what it saw. This 9 looks like a lowercase a. Not really sure what the writer was doing here when they gave this sample, but I can see why that would be called a 0. It's basically a big round circle with a slight touch on it. This 4 is basically a big smudge. I can see that it would struggle to call this anything, and it's even closed on top, which could make it look a lot like a 9. This 9, again, open loops. Actually, both of these next two examples are 9s that are called 4s. Doesn't close the loop on top, and perhaps a neural network sees that and says, oh, probably a 4. I don't know. I actually don't know how that's a 5. I would call that a 6 too. This I wouldn't call, I don't know what I would call that. Probably not 2 though. So again, really good performance across the board on these models, and they're only really getting confused on stuff that would honestly probably fool a lot of humans. It wouldn't have 100% agreement across people who could read these digits. So in summary, just kind of wrapping things up, model performance did increase with complexity, but my results exploration seems to indicate that simply adding layers wasn't the best approach, or isn't the best approach to improving classification accuracy. Doubling the convolutional layers from the simple model from 2 to 4 in the deeper model only improved performance marginally, and both models still made many of the same errors, meaning they probably converged to similar weights along their layers. The most complex model performed best, as I mentioned, but if I had to guess, it's not because of the additional 3 convolution layers and the additional convolution block. Rather, if I had to guess, it's probably because of batch normalization and dropout to prevent overfitting. I probably should have tested an intermediate model that had the same architecture as the deeper model, but with added regularization and dropout. That would have been pretty interesting to see the results from, but unfortunately did not include that. And just while we're talking about future steps, it would be pretty hard to squeeze any additional performance out of this, I think. Only 40 misses from a set of 10,000 tests is pretty good on the scores, especially with some of the digits in the test data that I really wouldn't be able to classify just as a person. So if we're going to talk about improving the model, perhaps improving efficiency is something we could talk about. I would definitely start by cutting back on the number of training cycles to prevent the risk of overfitting, and I would just do this by implementing early stopping. I would put in my training loop, if you see the training loss hit 0, then you're done. You have no more loss to achieve on your training group. I think that would save some of our precious environment. Thinking about increasing performance, I think the only way I would really approach this, and with any expectation, would be to train an ensemble with varied architecture as opposed to adding additional layers. It's hard to say if this would be worth it, given the increase in computation required, more than doubling or tripling if you're training 2 or 3 models to use in your ensemble. So, and again, it's important to consider the environmental impact of training machine learning models, but that's a different discussion for a different time. Anyway, with all that said, thanks everyone for stopping in. If you're watching this on YouTube, you can find a link to the project on my GitHub in the description. The notebook is much more fleshed out. You'll be able to actually see the code used to generate all of this, and I go into a little bit more in depth with my descriptions of things and my justifications. And if you're watching this anywhere else, you can find my GitHub here, Rahul Jean, and this is the MNIST digit classification. Anyway, thanks everyone for listening, and have a good day.